Okay, sorry for this. Yeah, okay, so Merker Patricia 3, MPT. I will just start with with the JSON that is returned by a get proof call. It contains two proofs. One is account proof, and the other one is storage proof. So in the account proof, there are some RLP streams. Each one of them is a branch or extension node, but extension node is just a special case of a branch. And each of these branches, each of these rows is a branch, and which contains 16 children, basically hashes of these children. So there are 16 substreams, each of 42 length. And so for example, the second one, if you hash the second row, you get one of the values in the first row. And it's at the position from one of the 0 to 15, and this position is determined by the account address. So the account address is, once it is hashed, it is 32 bytes long, and then this is converted into nibbles. So each byte is 2 nibbles from 0 to 15 value, and these nibbles determine the positions of the elements in their parent elements. So, but the last one, the last row, is account leaf, which contains this information here: balance, code hash, nonce, and the root of a storage tree. And then the situation is similar in storage proof. We again have some branches, like this is the root branch in storage tree, and it's only one in this case. And this is storage leaf, which contains key and value. In this case, value is 1. The key is what is in this case, for example, there's only one nibble used because there's only one branch, and the remaining 63 nibbles are stored in leaf. So the general idea of the circuit is we put each branch into 16 rows, and then each of these 16, the hash of these 16 rows is computed. It should be a bit colored, but it's not. The blocks are not clearly seen here. But so, for example. Yeah, this is one block, and the hash of this block in 16 rows needs to be at the proper position in the parent branch, and this position is given by nibbles. Yeah, in the circuit we actually have two proofs in parallel. So on the left side, there is a proof, a kind of a read operation. So what was the state before the storage modification, and on the right side there is a state or the proof for the state after the storage operation. So this is a proof of one storage operation for a storage modification at some particular key, and this key is the same for both of these two parallel proofs, and the circuit makes sure that both proofs are the same in most of the rows, except at the rows which are given by these nibbles. So there is an additional column called modified node. So that means the position of the children in this branch, and so these two proofs differ at these rows. Yeah, and once we arrive to the account leaf, the hash of the account leaf is computed and checked to be in the parent branch. And when we move to the storage tree, the hash of the root branch needs to be, we check that it's in the account leaf. So that's the basic idea. But yeah, if we zoom in a bit into the branch block, this is a block of one branch. It actually contains 19 rows, not 16, because there's an additional data. So, for example, in branch init, there are some RLP metabytes like this 249. This specifies the length of the branch, and it's sometimes these metabytes are of length 3 and sometimes of length 2. So there's some branching needed to correctly check the things. So the branch is put into 16 rows. So the first two, for example, are not empty here. The third one is empty. It only has this 128 value, which is some specifics of the RLP encoding. And in case when this is not a regular branch but an extension node, there are two additional rows, which I'll cover just in a second. So usually when there's a regular branch, the random linear combination of these bytes is computed, and then a lookup is made into Keccak circuit to check whether this RLC corresponds to the RLC of this hash, in this case at the position 15. But in the extension node case, it's a bit different. In this case, we need to check that the extension node is kind of branch where the path is a bit longer to arrive to the branch. So there are some additional nibbles, and these nibbles are stored here. And then the hash of this branch is stored here. So there are constraints to check that the hash of this branch is stored here. And then we compute the RLC, the random linear combination of this extension node, and then this is checked. The hash of this needs to be in the branch above. Yeah, but that's not. These are not the only constraints that need to be checked. This parent thing. It also needs to be checked that the storage modification happens at the correct address and at the correct key. So what is the circuit is computing the RLC of the nibbles, and then this RLC of the address, for example, is compared to the address to check to be the correct one. But it makes it a bit difficult because these are nibbles, not bytes, and we are computing a random linear combination of bytes. So sometimes this nibble needs to be computed by 16 and the multiplication factor, and sometimes with it needs to be multiplied by 1. And if there would be only regular branches, that would be easier, because then this would be just alternating. So once you need to multiply by 16 and once you need to multiply by 1. But if there is some extension node in between, extension node have some additional nibbles, and when it has an odd number of nibbles, this alternation is broken. So there needs to be some additional branching for the constraints. Yeah, and when we arrive to the leaf, then this. So we were computing the RLC of the nibbles. So like this way, from this branch, from the first two branches, we get this value, and then the remaining nibbles are stored here, and we continue computing the RLC. But it's again, some branching is needed because these nibbles, the remaining nibbles, are stored here in a compressed format, and this format depends on how many, on whether there are odd or 11 or even number of nibbles. yeah, this is just shows how the storage leaf, it takes 2 rows for the C proof, for the left proof, and 2 rows for the right proof. And yeah, one of the things that need to be checked is so sometimes this is the length of the nibbles is it varies. So and because we are computing the RLC of this of leaf, we need to make sure that after the length is after the specified length of this stream is finished, then there are really zeros after this position. Yeah, and then there are quite some special cases. So, for example, sometimes when a new value is added to the tree, an existing leaf is replaced by a branch. So, for example, in this case, we have some leaf, which is the RLP is here, and it's inside this branch 0. But after a new value is added, this leaf is replaced on the right side by a branch. So here another branch appears. Yeah, and the circuit just uses some placeholder values at this side, and the constraints then goes like this. The storage on the right, the leaf on the right side needs to be checked. The hash of the leaf needs to be checked to be here at the proper position, and then the hash of this branch needs to be at this position where the branch was inserted. But on the right side, the hash of this leaf needs to go one level above, so needs to be there in branch 0. And there are some further constraints in these cases. So for example, it needs to be checked that in this branch there are only 2 leaves. Okay, one at the one leaf that was added by this new value, and one leaf that was previously in the branch 0 and that was replaced by a branch. Yeah, and also it needs to be checked that this new leaf, the leaf that drifted from branch 0 to this branch 1, has the same value as the leaf on the left side. So for this reason, there's an additional row where this information about this drifted leaf is given. Yeah, and another special case is when there was no value specified at some key, the get proof returns just branches, so there is no leaf. And in this case, again, there is just some placeholder values are used, and it needs to be checked that at this position, it's just empty row in the branch. Yeah, and analogously, there are cases when we are close to the account leaf. So, for example, if there is no branch, or if there is just a leaf in the if there is only one level in the storage tree, so there is no branch, then again. Oh no, yeah, it's if we are in the first level, we are not comparing, we are not checking the hashes to be in the parent branch, but in the account leaf. So for this, some additional branching is needed, and yeah, that's a similar case. So yeah, that would be it.